Hello! In this video, we'll create a terrain from scratch using PCGForge. We'll start with a completely flat landscape and transform it into a realistic mountain formation, using just a few nodes. Before we begin, let's take a look at our scene. As you can see, we only have an empty terrain object. It's completely flat, with no shape or detail at all. By the end of this video, this terrain will look completely different. Let's start by configuring the size of our terrain. I'll select the terrain object and open the inspector. Here, you can see the mesh resolution section. By default, it's set to 1000 by 1000, which is a bit too small for most projects. I'll increase it to 2048 by 2048. I'll also set the terrain height to 800, which determines how high the terrain can rise. Next, let's scroll down to the texture resolution section. Here I'm setting the Heightmap resolution to 2049 by 2049. This is important because PCGForge will automatically read this value through the terrain node, so we won't need to configure it manually later. With the terrain settings in place, we're ready to move on to the actual generation process. PCGForge is entirely graph-based. That means before we can create a terrain, we first need to build a generation pipeline, what we call a PCG graph. In the project panel, I'll navigate to my project folder and create a new PCG graph asset. I'll name it PCG_sample terrain. Once I double-click the asset, the PCGForge graph editor opens. Right now, we're looking at a completely empty canvas, ready for us to start building our terrain generation pipeline. Let's add our first node to the graph. I'll double-click on an empty area in the graph, which opens the node search window. I'll type terrain and select the first result. The terrain node has now been added to the graph. However, you'll immediately notice a warning in the inspector panel: binding key is empty. So what does that mean? PCGForge graph assets are completely independent from the scene. This allows the same graph to be reused across different scenes and different terrain objects. Because of that, the graph needs a way to know which terrain it should work with in the current scene. This connection is called a binding. Now let's switch back to the scene and create that connection. In the hierarchy, I'll right-click on an empty area and select PCGForge to PCG graph bindings. This adds a new object called PCG graph bindings to the scene. With the object selected, you'll see a terrain binding section in the inspector. I'll click the Add button to create a new binding entry. In the key field, I'll enter sample terrain. This is simply an identifier that we'll use to reference the terrain from within the graph, so you can choose any name you like. Next, I'll drag the terrain object from the scene into the terrain field. As soon as I do that, we can see the message, "One binding registered," appear. Perfect. The connection has been successfully established. We've now connected the terrain object to the PCG graph. Next, let's give it some shape. In PCGForge, terrain generation usually starts by creating a height map and then writing that height map back to the terrain. A height map is basically a grayscale map that stores the elevation of each point on the terrain. White areas represent higher elevations, while black areas represent lower elevations. I'll select Perlin Heightmap. This node generates a height map using the Perlin Noise algorithm, which is a classic choice for creating natural-looking hills, valleys, and organic terrain forms. Now we need to connect the bounds output from the terrain node to the bounds input on the Perlin Heightmap node. This connection is very important. It tells the Perlin node how large the generated height map should be. The terrain node reads this information directly from the actual terrain object, so everything stays automatically aligned with the scene. On the right side, you can see the parameters of the Perlin Heightmap node. There are a few important values here. Scale controls the overall size of the noise pattern. Lower values create smaller, more frequent hills, while higher values create broader, large-scale terrain forms. We now have a height map, but it hasn't been applied to the terrain yet. To do that, we need to add a Heightmap To Terrain node. I'll right-click on an empty area in the graph and type HD into the search box. The Heightmap To Terrain node appears immediately, so I'll select it. Now let's connect everything together. Connect the height map output from the Perlin Heightmap node to the Heightmap input on the Heightmap to Terrain node. Then connect the terrain output from the terrain node to the terrain input on the Heightmap to Terrain node. At this point, our pipeline is complete. The Perlin node generates the Heightmap, and the Heightmap To Terrain node writes that data directly to the Unity terrain. The pipeline is now complete, and now comes the exciting part. I'll click the Generate button. The terrain is shaped instantly. We now have the characteristic smooth hills and wide valleys created by Perlin Noise, and this is fully procedural. I haven't sculpted, painted, or drawn anything manually. The entire terrain is being generated from node connections and parameter values. Now let's get to the fun part. Let's see how changing a few parameters can completely change the character of the terrain. I'll select the Perlin Heightmap node and increase scale from 200 to 650. This makes the terrain feel broader and more massive. The hills become larger and the valleys become wider. Next, I'll increase octaves to 7. This adds more layers of noise, giving the surface smaller variations and extra detail. I'll also set amplitude to 550 and base height to 40. The base height shifts the entire terrain slightly upward, almost like a landmass rising above sea level. Let's generate the terrain again. The result is much more dramatic now. But something is still missing. These hills are still a bit too smooth. They don't yet have the sharp, rocky structure that we usually see in real mountain formations. So next, we're going to fix that by adding a different type of noise. To create sharper mountain ridges and rocky outcrops, we'll use a different type of noise, ridged noise. As the name suggests, ridged noise generates sharp, ridge-like formations, making it ideal for mountains and rugged terrain. I'll add a ridged noise Heightmap node to the graph. Just like before, I'll connect the bounds output from the terrain node to the bounds input on the ridged noise Heightmap node. This ensures that both Heightmap generators use the same terrain dimensions and remain perfectly aligned. At this point, we have two separate Heightmaps, one generated by Perlin Noise and another generated by ridged noise. The Perlin Heightmap provides the large-scale terrain shapes, while the ridged Heightmap adds sharper mountain features and rocky details. Now we need to combine these two Heightmaps into a single result. To do that, we'll add a Heightmap Blend node. I'll select Heightmap Blend from the node search menu. Now let's connect everything together. Connect the output of the Perlin Heightmap node to the Heightmap A input on the Heightmap Blend node. Then connect the output of the ridged Heightmap node to the Heightmap B input. Finally, connect the output of the Heightmap Blend node to the Heightmap To Terrain node. In the inspector, I'll set the blend mode to lerp and leave the weight value at 0.5. This blends the two Heightmaps together with equal influence. If the weight is closer to 0, the result will be dominated by the Perlin Heightmap. If it's closer to 1, the ridged Heightmap will have a stronger influence on the final terrain. With a value of 0.5, we get a balanced mix of both, combining the broad terrain shapes from Perlin Noise with the sharper mountain details from ridged noise. Let's generate the terrain once again. Now we're preserving the broad, large-scale shapes created by the Perlin Noise, while also introducing the sharp ridges and rocky details generated by the ridged noise. The combination produces a much more natural result. The terrain feels more organic, with stronger mountain features and a more realistic overall appearance. Let's fine-tune the ridge noise parameters a little further. I'll keep the scale at 600. This gives us a good balance between large mountain formations and surface detail. Next, I'll increase octaves to 6, which adds additional layers of detail to the terrain. I'll reduce gain to 0.8. This softens the ridge contrast slightly, creating smoother transitions and a more natural-looking result. Finally, I'll set offset to 1.2, which helps shape the ridge patterns and refine the overall mountain structure. Now let's generate the terrain again. Take a look at the result. Compared to the previous version, the terrain feels much more balanced, with a better blend of large-scale forms and detailed mountain features. Now let's take a look at the terrain from a few different angles. We have wide valleys, smooth slopes, and sharp rocky formations near the higher areas. And we achieved all of this with just a few nodes. This is the core strength of PCGForge, building complex terrain results through a simple, reusable graph-based workflow. Let's quickly recap what we've learned in this video. In PCGForge, terrain generation follows three simple steps. First, you introduce your terrain to the graph using a terrain node. Next, you generate terrain shapes using one or more heightmap nodes. Finally, you apply the result back to the terrain using a heightmap to terrain node. You can combine and blend as many heightmap layers as you need to create more complex and realistic terrain formations. In the next video, we'll take this terrain a step further by adding hydraulic erosion. Using the hydraulic erosion node, we'll simulate water flow, carve erosion channels, create natural valley patterns, and add sediment deposition, all with a single node. If you have any questions, feel free to leave them in the comments. Thanks for watching, and I'll see you in the next video.